Something extraordinary just happened that might change everything we thought we knew about our place in the universe. The James Webb Space Telescope, the most powerful eye humanity has ever built, has discovered not just one, but multiple worlds that could be better suited for life than Earth. These aren't just rocks floating in space. These are planets with atmospheres, with water, and with conditions that make scientists stop in their tracks and reconsider what we know about habitable worlds. Right now, as you watch this video, there are planets out there that might already be home to life, and we're finally able to see them clearly for the first time in human history. If you like the content, consider subscribing and leaving a like. Get ready, we begin. Chapter 1: The Revolutionary Power of James Webb. Before we dive into the incredible planets Webb has discovered, we need to understand what makes this telescope so special and why it represents such a massive leap forward in our ability to study the universe. The James Webb Space Telescope isn't just another telescope. It's a quantum leap forward in our ability to study distant worlds and search for signs of life beyond Earth. Its primary mirror is over 21 feet across, made of 18 hexagonal segments coated in gold. This massive mirror collects light that has traveled across unimaginable distances, light that carries information about worlds we could never have studied before. The gold coating on Webb's mirrors isn't just for show. Gold is an excellent reflector of infrared light, which is the type of light Webb is designed to observe. Infrared light has longer wavelengths than visible light, which means it can pass through clouds of dust that would completely block visible light. This is crucial for studying star-forming regions where new planets are being born, but it's equally important for studying exoplanets because infrared observations can reveal thermal emission from planets themselves, not just reflected light from their stars. By observing in infrared wavelengths, Webb can study planets in ways that visible light telescopes simply cannot. Webb operates primarily in infrared wavelengths, ranging from 0.6 to 28 microns. To put this in perspective, visible light that our eyes can see ranges from about 0.4 to 0.7 microns, so Webb can see light with wavelengths up to 70 times longer than what we can see. Different molecules absorb and emit light at specific infrared wavelengths, so by observing across this wide range, Webb can identify the chemical fingerprints of gases in planetary atmospheres. Water vapor, methane, carbon dioxide, ammonia, and dozens of other molecules all have unique signatures in the infrared, and Webb's instruments are sensitive enough to detect these signatures from planets that are hundreds of light years away. The telescope orbits the Sun at a point called Lagrange Point 2, or L2, which is about 1 million miles from Earth in the direction away from the Sun. This special location is a point of gravitational equilibrium, where the combined gravity of the Sun and Earth keeps Webb in a stable orbit that moves with Earth around the Sun. This position has several advantages. It keeps Webb in permanent shadow from the Sun, Earth, and Moon, which is essential because its instruments need to stay incredibly cold to function properly. The telescope has a massive sunshield the size of a tennis court with 5 layers of material, each thinner than a human hair. This sunshield keeps the sun-facing side at temperatures that can reach 230 degrees Fahrenheit, while the telescope side stays at -370 degrees Fahrenheit. This extreme cooling is necessary because Webb needs to detect faint infrared light from distant objects without being overwhelmed by its own heat signature. Everything with temperature emits infrared radiation, and at room temperature, Webb's own instruments would glow brightly in infrared, making it impossible to see faint distant sources. By cooling the instruments to just a few degrees above absolute zero, Webb minimizes this interference and achieves the sensitivity needed to study exoplanet atmospheres. The detectors in Webb's instruments are so sensitive that they could theoretically detect the heat signature of a bumblebee at the distance of the Moon. What makes Webb truly revolutionary for planet hunting is its ability to do spectroscopy, which is the science of breaking light down into its component wavelengths and analysing the pattern. When light passes through a prism or diffraction grating, it spreads out into a spectrum showing all the different wavelengths present. Different molecules absorb light at specific wavelengths, creating dark lines or bands in the spectrum where that wavelength is missing. These absorption features are like barcodes, unique patterns that identify specific molecules. When Webb analyzes the light that has passed through an exoplanet's atmosphere during a transit, it can identify the specific molecules present by looking at which wavelengths are absorbed. The technique works like this. When a planet passes in front of its star from our perspective, most of the star's light goes around the planet, but a tiny fraction passes through the thin shell of the planet's atmosphere at the edges. The molecules in that atmosphere absorb some wavelengths while letting others pass through. By comparing the spectrum of the star when the planet isn't transiting to the spectrum during the transit, astronomers can see which wavelengths were absorbed by the atmosphere. The difference between these two spectra reveals the atmospheric composition. The math and data analysis involved are incredibly complex, requiring sophisticated computer models and careful calibration, but the principle is straightforward. Webb has several scientific instruments, each optimized for different types of observations. The near-infrared camera, or NIR-CAM, is Webb's primary imager and can take incredibly sharp pictures in infrared light. The near-infrared spectrograph, or NIR-SPEC, can take spectra of up to 100 objects simultaneously, making it incredibly efficient for studying large numbers of stars or galaxies. The mid-infrared instrument, or MIRI, observes at the longest wavelengths and includes both a camera and a spectrograph. The near-infrared imager and slit-less spectrograph, or NIRIS, is particularly useful for exoplanet studies because it can take spectra of transiting planets with very high precision. Each of these instruments took years to develop and represents the cutting edge of detector technology. The sensors in these instruments are unlike anything in consumer cameras or even most scientific equipment. They can detect individual photons of infrared light and measure their wavelengths with incredible precision. Some of the detectors are made from mercury cadmium telluride, a semiconductor material that's sensitive to infrared light. Others use different materials optimized for specific wavelength ranges. All of them required new manufacturing techniques and years of testing to perfect. The data Webb collects is so detailed that scientists can not only detect the presence of different molecules, but also estimate their abundance. By measuring how strong the absorption features are at different wavelengths, astronomers can determine approximately how much of each gas is present in the atmosphere. This allows researchers to build models of what these alien atmospheres might actually be like. They can estimate temperature profiles showing how temperature varies with altitude, pressure levels at different heights in the atmosphere, and even make educated guesses about cloud coverage and weather patterns. The level of detail is extraordinary, and it's giving us our first real glimpses of the three-dimensional structure and dynamics of exoplanet atmospheres. Understanding what Webb can and cannot do is important for appreciating its discoveries. Webb cannot take pictures of Earth-sized planets orbiting sun-like stars at distances of dozens of light years. The planets are simply too small and too close to their much brighter stars for even Webb to separate them. What Webb can do is study planets when they transit in front of their stars, using the transits as opportunities to probe the atmospheres. Webb can also directly image some large planets that orbit far from their stars, where the planet's light can be separated from the starlight. These directly imaged planets tend to be young, massive, and hot, making them bright enough in infrared to be detected despite the glare from their stars. The construction and deployment of Webb itself is a story of engineering triumph. The telescope was too large to fit in any rocket in its final configuration, so it had to be designed to fold up for launch and then deploy once in space. The primary mirror segments had to unfold and lock into place with microscopic precision. The sun shield had to unfurl and tension its 5 layers into the exact configuration needed for thermal control. Over 300 single-point failures could have doomed the mission, events where if one thing went wrong, the entire telescope would be lost. The deployment sequence involved 50 major steps and took 2 weeks to complete. When the final component locked into place and Webb began commissioning, the relief among the scientists and engineers who had devoted decades of their lives to the project was palpable. Webb's location at L2 also means that it's too far away for a repair mission by astronauts, unlike the Hubble Space Telescope, which was serviced multiple times by space shuttle crews. Everything has to work perfectly because there's no second chance. The telescope was designed with redundancy for critical systems, and it carries enough fuel to maintain its orbit and orientation for at least 20 years, possibly longer, with careful management. Every observation is precious, and the time on Webb is allocated through a competitive process where astronomers from around the world propose observations, and a panel of experts decides which projects are most scientifically valuable. The telescope officially began science operations in July 2022, and the first images released to the public showcased Webb's incredible capabilities. There was the deepest infrared image of the universe ever taken, showing galaxies as they appeared over 13 billion years ago. There were stunning images of nebulae where stars are being born, revealing structures never seen before. And there were the first spectra of exoplanet atmospheres taken by Webb, showing clear detections of water vapor and hints of clouds and hazes. These early results proved that Webb was working even better than expected and set the stage for the discoveries that would follow. Chapter 2. K2-18b, the ocean world. That changed everything among all the exoplanets Webb has studied. One stands out as particularly extraordinary and has captured the imagination of astronomers and the public alike. Scientists call it K2-18b, and this world has become the poster child for potentially habitable exoplanets and the search for life beyond Earth. Located about 120 light-years away in the constellation Leo, this planet orbits a cool dwarf star, smaller and dimmer than our Sun, in what astronomers call the habitable zone. That's the region around a star where temperatures are just right for liquid water to exist on a planet's surface, the single most important prerequisite for life as we know it. But K2-18b isn't just in the habitable zone. The data from Webb suggests it might actually be covered in a vast global ocean, making it a true water world. K2-18b is substantially larger than Earth, with a radius about 2.6 times that of our planet and a mass nearly 9 times greater. This makes it what scientists call a sub-Neptune, a category of planet that doesn't exist in our solar system but appears to be incredibly common throughout the galaxy. We have small rocky planets like Earth, Mars, Venus, and Mercury, and we have giant planets dominated by hydrogen and helium like Jupiter, Saturn, Uranus, and Neptune, but we don't have anything in between. The gap in our solar system between Earth at 1 Earth mass and Uranus at 14.5. Earth masses contains no planets. Yet when we look at other star systems, we find that this gap is actually the most populated region. Sub-Neptunes and super-Earths, planets with masses between 1 and 10 times Earth's mass, are the most common type of planet in the galaxy. This unexpected abundance of sub-Neptunes raised important questions. Are these planets more like scaled-up versions of Earth, with rocky surfaces and potentially breathable atmospheres? Or are they more like scaled-down versions of Neptune, with thick hydrogen atmospheres that make them fundamentally different from terrestrial planets? The answer matters enormously for habitability, because a thick hydrogen atmosphere would create crushing surface pressures and wouldn't be breathable by life as we know it. For years, this question remained unanswered because we simply didn't have the tools to study sub-Neptune atmospheres in enough detail. K2-18b is changing that. When Webb turned its powerful instruments toward K2-18b in 2023, what it found was remarkable and has been the subject of intense scientific scrutiny and debate ever since. The telescope detected strong signatures of both methane and carbon dioxide in the planet's atmosphere. The presence of these molecules told scientists that K2-18b's atmosphere is not dominated by hydrogen. If it were, the hydrogen would prevent methane and CO2 from leaving such strong signatures. Instead, the atmosphere appears to be hydrogen-rich but not hydrogen-dominated, a subtle but crucial distinction. This finding suggested that K2-18b might be something we've never seen before in our solar system, a type of world that theoretical models predicted but that we'd never confirmed. Even more intriguing and controversial is the hint of a molecule called dimethyl sulfide, or DMS. The initial data suggested that DMS might be present in K2-18b's atmosphere, though the signal was weak and at the edge of Webb's detection capabilities. This finding sent waves of excitement through the scientific community because on Earth, DMS is almost exclusively produced by living organisms, particularly phytoplankton in our oceans. When phytoplankton break down a sulfur-containing molecule called DMSP, one of the products is DMS, which then escapes into the atmosphere. In fact, DMS is responsible for much of what we think of as the smell of the ocean. The possibility that K2-18b might have DMS in its atmosphere raised the tantalizing prospect that we might be detecting our first biosignature, a chemical signature of life, on another world. However, scientists are approaching this finding with appropriate caution. The detection of DMS is preliminary and needs to be confirmed with more observations. Webb has been scheduled to observe K2-18b again to get more data and either confirm or refute the presence of DMS. Even if DMS is confirmed, scientists would need to rule out any possible non-biological sources before claiming it as evidence of life. On Earth, DMS can also be produced by volcanic activity, though in much smaller amounts than biological processes create. Some chemical reactions in the atmosphere or on the surface might also produce DMS-like signals that could be mistaken for the actual molecule. The standards of evidence for claiming the discovery of extraterrestrial life are rightfully extremely high. The temperature on K2-18b appears to be remarkably temperate based on models of its atmosphere and energy balance. The planet receives about 25% as much radiation from its star as Earth receives from the Sun. This initially sounds like it might be too cold, but the actual surface temperature depends heavily on the atmosphere's composition and thickness. Greenhouse gases like methane and carbon dioxide trap heat, warming the planet above what it would be with no atmosphere. The models suggest that K2-18b could have surface temperatures somewhere between the freezing and boiling points of water, exactly the range where liquid oceans could exist. Some models suggest average temperatures around 10 to 20 degrees Celsius, similar to Earth's oceans. Scientists believe that K2-18b might be what they call a Hycean world, a theoretical type of planet that was proposed before Webb ever observed one. The term Hycean combines hydrogen and ocean, describing a planet that has a hydrogen-rich atmosphere sitting above a global water ocean. The hydrogen atmosphere would be much thicker than Earth's atmosphere, but beneath it there would be a distinct transition to liquid water. In this model, the hydrogen atmosphere acts like a thick blanket, trapping heat and maintaining moderate temperatures at the ocean surface, despite the relatively weak sunlight the planet receives from its dim red dwarf star. If this model is correct, K2-18b could have ocean depths measured in hundreds of kilometers, far deeper than Earth's deepest ocean trench, which goes down about 11 kilometers. The pressure at those depths would be immense, millions of times greater than atmospheric pressure at Earth's surface. Under such extreme pressure, water doesn't behave like the water we're familiar with. At sufficiently high pressures and depending on temperature, water can turn into exotic forms of high-pressure ice that remain solid even at temperatures above the normal boiling point. Some models suggest that K2-18b might have layers of these high-pressure ices at the bottom of its ocean, with the liquid ocean sandwiched between the gas atmosphere above and the solid high-pressure ice below. The question of whether life could exist in such an environment is fascinating to contemplate. On Earth, we've found life in virtually every environment that has liquid water, from boiling hot springs to the coldest ocean waters, from the most acidic lakes to the most alkaline soda lakes, and from the brightest sunlit shallows to the darkest ocean depths. The deep oceans of Earth, beyond the reach of sunlight, host thriving ecosystems based not on photosynthesis, but on chemosynthesis, where microbes extract energy from chemical reactions involving hydrogen sulfide or methane seeping from the ocean floor. If K2-18b has a global ocean, there could be chemical energy sources from interactions between the water and the rocky interior below, potentially providing energy for life. The gravity on K2-18b would be noticeably stronger than Earth's, roughly 1.9 to 2.1 times what we experience, depending on exactly what the planet's internal structure is like. This means that if you could somehow stand on a solid surface there, which might not even exist if it's a true water world, you would weigh twice as much as you do on Earth. A person who weighs 150 pounds on Earth would weigh about 300 pounds on K2-18b. This stronger gravity would also have implications for any life that might exist there. Larger organisms would need stronger structures to support themselves against the pull of gravity. Swimming might be easier in some ways because buoyancy still works the same way, but emerging onto land, if land exists, would be much more challenging for large creatures. However, stronger gravity also provides advantages for habitability. A planet with stronger gravity can hold onto its atmosphere more effectively, preventing gas molecules from escaping to space. This is especially important for planets orbiting red dwarf stars, which tend to be very active in their youth, producing frequent and powerful flares that can strip away planetary atmospheres. K2-18b's relatively large mass means that even if its star was very active early in its history, the planet likely retained most of its atmosphere thanks to its strong gravitational grip. This atmospheric retention over billions of years is crucial for maintaining habitable conditions. One of the most encouraging aspects of K2-18b from a habitability perspective is that its host star is a red dwarf, specifically a star classified as type M3V. Red dwarf stars are much smaller and cooler than our Sun, but also much more numerous and much more long-lived. While our Sun will have a total lifespan of about 10 billion years, spending roughly 10 billion years as a stable main sequence star before beginning its transformation into a red giant, red dwarf stars can burn their hydrogen fuel for trillions of years. This is because red dwarfs are so much less massive than the Sun that they burn their fuel much more slowly. Some of the smallest red dwarfs could theoretically shine for longer than the current age of the universe, though the universe isn't old enough yet for any red dwarf to have died of old age. This extraordinary longevity means that if life did get started on K2-18b, it would have enormous amounts of time to evolve and develop. Life on Earth took about 3.5 to 4 billion years to go from the first simple cells to complex multicellular organisms, and about 4.5 billion years total to go from a sterile planet to a civilization capable of building telescopes and studying other worlds. On a world like K2-18b, orbiting a red dwarf, there could be tens or even hundreds of billions of years for similar processes to unfold. If a life tends to follow similar evolutionary paths given enough time, planets around red dwarfs might eventually host civilizations far more advanced than ours, simply because they've had so much more time to develop. Of course, this assumes that red dwarf stars don't pose unsurmountable challenges for life. Young, red dwarfs are known to be very active, producing frequent stellar flares that temporarily increase the star's brightness by factors of 10 or more and send out intense bursts of ultraviolet and X-ray radiation, along with streams of charged particles. For a planet orbiting close to a red dwarf, as planets in the habitable zone must do because red dwarfs are so dim, these flares could repeatedly bathe the planet in harmful radiation. The charged particles could also interact with the planet's atmosphere, potentially causing atmospheric erosion over millions of years. However, K2-18b's specific star appears to be relatively calm as red dwarfs go. Observations have detected some flare activity, but not at the extreme levels seen around the most active red dwarfs. Additionally, the planet's thick atmosphere would provide significant shielding for any life in the ocean. Water is an excellent radiation shield, with just a few meters of water providing protection equivalent to Earth's entire atmosphere and magnetic field. If K2-18b is truly an ocean world, any life below the surface would be well protected from stellar flares. The orbital period of K2-18b is about 33 Earth days, meaning a year on K2-18b is just over a month long by our calendar. The planet is almost certainly tidally locked to its star, meaning one face of the planet always points toward the star, while the other face always points away, just as the same side of the Moon always faces Earth. This tidal locking is a natural consequence of orbiting so close to a star, and happens because the gravitational tidal forces from the star cause one side of the planet to always bulge slightly toward the star. Over millions of years, this tidal interaction slows the planet's rotation until it matches the orbital period. Tidal locking has important implications for the climate. Without rotation, you don't get the Coriolis effect that drives Earth's weather patterns, and you do get extreme differences between the day side and night side. However, if the atmosphere is thick enough, which appears to be the case for K2-18b, winds will circulate heat from the day side to the night side, moderating the temperature differences. For an ocean world, the water itself provides an enormous thermal mass that resists rapid temperature changes. The day side might be somewhat warmer and the night side somewhat cooler, but the differences wouldn't necessarily be extreme. Some scientists speculate that a tidally locked ocean world might have fascinating weather patterns with permanent storm systems at certain locations and regions of relative calm elsewhere. The discovery of K2-18b and the detailed analysis Webb has provided represent a watershed moment in the search for life beyond Earth. For the first time, we're not just finding planets that might be habitable based on their size and distance from their star. We're actually able to study their atmospheres in enough detail to look for the kinds of chemicals that might indicate biological activity. We can measure temperature, pressure, and composition. We can detect individual molecules and track how their abundances change. K2-18b might not have life, The DMS detection might turn out to be a false alarm, a misinterpretation of the data, or an artifact of the way the atmosphere scatters light. But the fact that we can even ask this question based on real data rather than pure speculation is extraordinary. This is the beginning of a new era in astronomy where we can actually start to answer the ancient question of whether we're alone in the universe with observations rather than philosophy. Chapter 3. LHS 1140b, the super-Earth in the perfect zone. While K218b captures headlines with its potential ocean and possible biosignatures, another world has scientists equally excited and perhaps even more optimistic about finding true Earth-like habitability. Meet LHS 1140b, a planet that many researchers now consider to be the single most promising habitable world candidate we've discovered so far. This planet, located about 40 light-years away in the constellation Cetus the Whale, has several characteristics that make it exceptionally interesting in the search for life beyond Earth, and a prime candidate for intensive study with Webb and future telescopes. LHS 1140b was discovered in 2017 using the radial velocity method, where astronomers detect planets by measuring the tiny wobble they cause in their star's motion as planet and star orbit their common center of mass. The planet is classified as a super-Earth, which means it's larger and more massive than our planet, but not so large that it becomes a gas or ice giant. With a radius about 1.7 times that of Earth and a mass roughly 5.6 times greater, this world offers substantially more real estate and resources than our home planet while still maintaining the rocky composition necessary for the kind of surface chemistry that supports life as we know it. The planet's density, calculated from its mass and radius, is consistent with a rocky composition similar to Earth, likely with an iron core, a silicate mantle, and possibly a thin veneer of water. What really sets LHS 1140b apart and makes it the focus of so much scientific attention is its position in what astronomers call the conservative habitable zone, sometimes also called the empirical habitable zone. While many planets are in the broader optimistic habitable zone, where conditions might allow for liquid water under certain special circumstances or with particular atmospheric compositions, LHS 1140b sits right in the sweet spot where liquid water on the surface is highly likely regardless of reasonable variations in atmospheric composition. The conservative habitable zone is defined based on Venus and Mars in our solar system, representing the region where we're very confident liquid water can exist. The planet orbits a red dwarf star designated LHS 1140 that's about 1/5 the size of our Sun and about 0.15% as luminous. This means that to receive enough warmth for habitability, a planet must orbit much closer to LHS 1140 than Earth orbits the Sun. LHS 1140b completes one orbit every 24.7 Earth days, meaning a year on this planet is shorter than a month on Earth. Despite this close orbit, the low luminosity of the star means the planet receives only about 43% as much stellar energy as Earth receives from the Sun. This is more than enough to maintain liquid water with the right atmosphere, but it's not so much that the planet would be at risk of a runaway greenhouse effect like Venus. When Webb studied LHS 1140b, the data revealed something fascinating and unexpected about this world's atmosphere. Unlike many other planets in this size range that turned out to have thick hydrogen or helium atmospheres that would make them more like mini Neptunes than super-Earths, LHS 1140b appears to have lost most or all of any primordial hydrogen atmosphere it might have once had. This is excellent news for habitability because a thick hydrogen atmosphere would create tremendous surface pressures and wouldn't support the kind of chemistry necessary for life as we know it. Instead, the planet appears to have what scientists call a secondary atmosphere, one created by volcanic outgassing or possibly delivered by comet impacts, rather than captured directly from the protoplanetary disk during formation. The composition of this secondary atmosphere is still being studied, but initial data suggests it could potentially include nitrogen, oxygen, carbon dioxide, and water vapor, which is exactly the kind of mix you would want to find on a habitable world. On Earth, nitrogen makes up about 78% of our atmosphere and provides a stable, non-reactive background gas. Oxygen makes up about 21% and is essential for the metabolism of most complex life. Carbon dioxide is present in much smaller amounts, less than 1%, but plays a crucial role in regulating temperature through the greenhouse effect. Water vapor varies from place to place and provides clouds, rain, and another important greenhouse effect. If LHS 1140b really does have a similar atmospheric composition, it would be remarkably Earth-like, despite being so much larger. The presence of significant oxygen in an atmosphere is particularly significant and potentially controversial because oxygen is highly reactive chemically. In a planetary atmosphere without life, oxygen quickly combines with rocks, dissolved iron in oceans, volcanic gases like hydrogen sulfide and carbon monoxide, and organic molecules produced by non-biological chemistry. On a lifeless planet, any oxygen in the atmosphere should disappear within a few million years, which is geologically very rapid. On Earth, oxygen built up in our atmosphere about 2.4 billion years ago in an event called the Great Oxidation Event, and this oxygen came entirely from photosynthetic cyanobacteria that produce oxygen as a waste product. Today, plants, algae, and photosynthetic bacteria produce oxygen that constantly replenishes our atmosphere and maintains the 21% oxygen level we need to breathe. If LHS 1140b really does have significant oxygen in its atmosphere, that would be a very strong hint that something biological might be happening there, though not proof. There are some abiotic processes that can produce atmospheric oxygen, particularly photolysis of water vapor, by ultraviolet light from the star, which splits water molecules into hydrogen and oxygen. The light hydrogen can escape to space while the heavier oxygen remains in the atmosphere. This process could potentially produce an oxygen-rich atmosphere on a planet that has a lot of water and receives a lot of ultraviolet light. However, scientists have models for how much oxygen these abiotic processes can produce. And if LHS 1140b has oxygen levels significantly exceeding those predictions, biology becomes a much more attractive explanation. Temperature models suggest that LHS 1140 Borwalk could have surface temperatures quite similar to Earth, perhaps averaging around 10 to 20 degrees Celsius across much of the planet, which would be cool but comfortable. Some regions might be warmer and others cooler, depending on atmospheric circulation patterns, cloud coverage, and whether there are oceans or continents. This temperature range is cool enough that water wouldn't boil away even at low atmospheric pressures, but warm enough that the planet wouldn't be frozen into a permanent snowball state. The moderate temperatures would allow for a water cycle with evaporation from oceans or lakes, cloud formation, precipitation as rain or snow, and runoff back into bodies of water, much like Earth's water cycle. Some models even suggest the planet could be partially covered by a global ocean with ice caps at the poles, similar to Earth, but perhaps with a different ratio of land to water. The exact surface conditions depend on factors we can't yet measure directly, like how much water the planet actually has, how its interior heat production compares to Earth's, whether plate tectonics is active, and how any continents might be arranged. A planet with more water than Earth might have shallower oceans spread over more of the surface, while a planet with less water might have deeper oceans confined to basins between larger continents. The possibilities are intriguingly varied. One of the key reasons LHS 1140b is considered such a promising target for the search for habitable conditions is that it likely retained its atmosphere over billions of years despite orbiting a red dwarf star. This is not a given for planets around red dwarfs. Many planets orbiting red dwarf stars lose their atmospheres early in their history because young red dwarfs tend to be very active and violent, firing off powerful flares and producing strong stellar winds full of charged particles that can strip away a planet's air. The process is called atmospheric erosion, and it can render potentially habitable planets lifeless and barren if it removes too much atmosphere too quickly. However, LHS 1140b has several factors working in its favour. First, its relatively large size and strong gravity help it hold onto its atmosphere even in the face of stellar activity. The escape velocity from LHS 1140b is about 2.5 times that of Earth, meaning gas molecules would need 2.5 times as much energy to escape to space. This makes atmospheric retention much easier. Second, the star LHS 1140 appears to be relatively quiet compared to many other red dwarfs. While all red dwarfs have periods of high activity, especially when they're young, LHS 1140 seems to be in a calmer phase of its life. Observations have detected some flare activity, but not at the extreme levels that would pose the most serious threat to atmospheric retention. Third, LHS 1140b's relatively large mass means it probably had more volcanic activity early in its history, releasing gases from its interior that could rebuild the atmosphere if some was lost to space. Volcanic outgassing releases water vapor, carbon dioxide, nitrogen, and other gases from a planet's interior. On Earth, volcanic activity played a crucial role in creating our atmosphere and continues to influence atmospheric composition today. A larger planet with a hotter interior would have even more vigorous volcanic activity, at least early in its history, providing a robust mechanism for atmospheric replenishment. The question of whether LHS 1140b has a magnetic field is crucial but currently unknown. Earth's magnetic field, generated by the motion of liquid iron in our planet's outer core, creates a protective bubble called the magnetosphere that deflects most of the charged particles from the solar wind and shields our atmosphere from erosion. Mars, by contrast, lost most of its magnetic field early in its history, and this loss is thought to be a major reason why Mars subsequently lost most of its atmosphere and became the cold, dry planet we see today. If LHS 1140b has a liquid iron core generating a magnetic field, this would provide additional protection for the atmosphere and make long-term habitability more likely. The planet's relatively large iron core, inferred from its overall density, suggests that a magnetic field is plausible, but we won't know for certain until we can make more detailed observations. The orbital characteristics of LHS 1140b present both advantages and challenges for potential habitability. Because the planet is so close to its star, completing an orbit in less than 25 days, it's very likely tidally locked, meaning the same side always faces the star while the opposite side always faces away into eternal night, just as the same side of the moon always faces Earth. This would create a permanent day side and a permanent night side with very different conditions. The day side, where the star never sets and hangs perpetually in the sky, would be warm and bright. The night side, where the star never rises and the sky is always dark except for any moons or distant stars, would be cold and frozen. However, if the planet has a thick enough atmosphere, which the data suggests it does, winds would circulate heat from the day side to the night side, moderating the temperature differences and potentially creating habitable conditions across much of the planet. On Earth, atmospheric circulation driven by temperature differences, and the Coriolis effect from our planet's rotation creates wind patterns that redistribute heat from the equator to the poles. On a tidally locked planet, the circulation would be different, driven by the temperature difference between day and night sides rather than equator and poles, but it would still work to even out temperatures. Some scientists have speculated that tidally locked planets might have a particularly interesting habitable zone in the twilight region, the ring around the planet between permanent day and permanent night, where the sun sits perpetually at or near the horizon. In this twilight zone, the sunlight would be dim, arriving at a low angle, but temperatures might be more moderate than either the bright hot day side or the dark frozen night side. This region could be a comfortable environment for life, with interesting possibilities for day-night cycles, driven not by the planet's rotation, but by moving between regions with slightly different sun angles. Another consideration is the possibility of moons. If LHS 1140b has one or more moons, these satellites could create tides in any oceans, mixing nutrients and potentially providing additional complexity to the environment. Moons could also provide additional bodies that might themselves be habitable, especially if tidal heating from the planet's gravity keeps them warm. In our own solar system, some of the most promising places to look for life are moons like Europa, Enceladus, and Titan, rather than planets. If a large rocky planets like LHS 1140b commonly have moons, this would multiply the number of potentially habitable environments. Future observations with Webb and other telescopes will be crucial for determining just how Earth-like LHS 1140b really is, and whether it deserves its status as the most promising habitable world yet found. Scientists have proposed and been granted additional Webb observation time to study LHS 1140b in more detail, searching for additional molecules in the planet's atmosphere and trying to map how temperature and composition vary across the planet's surface. If these observations confirm the presence of oxygen, nitrogen, carbon dioxide, and water vapor in the right proportions, LHS 1140b will cement its position as the prime target in the search for life beyond our solar system. The planet is also close enough and bright enough that we can study it in considerable detail with existing and near-future technology, but far enough that we're truly looking at an alien world rather than something in our immediate cosmic neighborhood. At 40 light-years away, the light we receive from LHS 1140b today actually left the planet in 1985, during the Reagan administration and the height of the Cold War. When we observe this planet, we're seeing it as it was decades in the past due to the finite speed of light. If there are any observers on LHS 1140b with technology similar to ours looking back at Earth, they would be seeing Earth as it was in the mid-1980s. The study of LHS 1140b represents everything exciting about modern exoplanet science. We're not just cataloguing planets or checking boxes about their basic properties. We're doing detailed characterization, building up atmospheric profiles, searching for biosignatures, and seriously grappling with the question of whether these worlds might host life. Every new observation of LHS 1140b adds to our understanding and brings us closer to answering whether this world is truly Earth's twin in another solar system, or whether subtle differences make it less habitable than it first appears. Either way, the knowledge we gain will transform our understanding of habitable planets and guide the search for life beyond Earth for decades to come. Chapter 4: The TRAPPIST-1 System, 7 Worlds of Wonder. While individual planets like K2-18b and LHS 1140b are extraordinary, perhaps nothing captures the imagination and represents the diversity of potentially habitable worlds, quite like the TRAPPIST-1 system. This remarkable stellar system located about 40 light-years away in the constellation Aquarius, contains not one, not two, but 7 Earth-sized planets orbiting a single ultra-cool red dwarf star. 3 of these 7 worlds orbit in the habitable zone where liquid water could exist, and the entire system is compact enough that all 7 planets orbit closer to their star than Mercury orbits our Sun. The James Webb Space Telescope has begun the painstaking work of studying each of these planets individually to understand which, if any, might harbour the conditions necessary for life. The TRAPPIST-1 system is like a natural laboratory where we can compare multiple similar planets under different conditions and see how orbital distance affects habitability. The TRAPPIST-1 system is unique in our catalogue of known exoplanets for several reasons. The central star is only slightly larger than Jupiter in diameter, though it's about 80 times more massive, just barely massive enough to sustain hydrogen fusion in its core and qualify as a true star rather than a brown dwarf. Despite being so small, the star will burn its hydrogen fuel so slowly that it will shine for trillions of years, far longer than the current 13.8 billion year age of the universe. The star's mass is only about 9% that of our Sun, and its luminosity is less than 1% of the Sun's. This extreme faintness means that for a planet to be warm enough for habitability, it must orbit very close indeed. The 7 planets labelled TRAPPIST-1b through TRAPPIST-1h in order of increasing distance from the star orbit incredibly close by the standards of our solar system. TRAPPIST-1b, the innermost planet, orbits in just 1.5 Earth days at a distance of only 1.7 million kilometres from the star. For comparison, Mercury orbits the Sun at an average distance of 58 million kilometres. The outermost planet, TRAPPIST-1h, takes about 19 Earth days to complete one orbit. If you could stand on any of these planets and look up at the sky, the star would appear enormous, much larger than our Sun appears from Earth. But it would glow with a deep ruddy red colour rather than the yellow-white we're used to seeing. The star would provide about as much light as dim twilight on Earth, requiring eyes adapted to low-light conditions to see well. The 3 planets in the habitable zone, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, are of particular interest to astrobiologists and are receiving the most attention from Webb observations. TRAPPIST-1e is considered the most Earth-like of the bunch, and arguably one of the most Earth-like exoplanets yet discovered. With a radius about 92% that of Earth, and a density suggesting it has a substantial iron core and a rocky silicate mantle similar to our own planet, TRAPPIST-1e looks remarkably like Earth in terms of its basic physical properties. The planet receives about 66% as much stellar energy as Earth receives from the Sun, which is enough to maintain moderate surface temperatures with the right atmosphere. TRAPPIST-1f is slightly larger and less dense than TRAPPIST-1e, suggesting it might have more water as a fraction of its total mass. This planet receives about 38% as much stellar energy as Earth, putting it on the cooler end of the habitable zone. Depending on its atmosphere, TRAPPIST-1f might be covered in water ice or liquid water, or it might have a mix of icy caps and temperate seas. TRAPPIST-1g is the largest planet in the system and sits on the outer edge of the habitable zone, receiving only about 25% as much stellar energy as Earth. This planet would require a thick atmosphere with significant greenhouse warming to maintain liquid water, but such conditions are certainly possible. Each planet represents a different experiment in planetary habitability, variations on a theme where we can study how different levels of stellar irradiation affect conditions on otherwise similar worlds. The beauty of having all 7 planets in one system is that they presumably formed from the same protoplanetary disk, and thus likely have similar initial compositions and formation histories. Any differences we observe in their atmospheres and surface conditions are probably due to their different orbital distances and the different amounts of energy they receive from their star. This makes the TRAPPIST-1 system an ideal natural laboratory for comparative planetology. Webb's observations of the TRAPPIST-1 planets have yielded both exciting results and some disappointments, painting a complex picture of which worlds might be habitable and which face insurmountable challenges. Early observations focused on TRAPPIST-1b, the innermost planet, which was expected to have lost any atmosphere long ago due to the intense radiation it receives from being so close to the star. Webb's observations confirmed this expectation, finding no evidence of a substantial atmosphere. The data was consistent with a bare rock surface, heavily irradiated and likely with temperatures hot enough to melt certain minerals. While this result wasn't surprising, it provided a valuable calibration of Webb's capabilities and confirmed our understanding of how stellar radiation affects close-in planets. TRAPPIST-1c, the second planet from the star, also appears to have lost most or all of its atmosphere based on Webb observations. This planet is just outside the region where we expect all atmospheres to be completely stripped away, making it a crucial test case. The absence of a substantial atmosphere on TRAPPIST-1c suggests that the habitable zone around ultra-cool dwarfs like TRAPPIST-1 might not extend as close to the star as some models predicted. It tells us that even though these stars are cool and dim, they can still strip away planetary atmospheres through a combination of intense ultraviolet radiation when the star is young, and possibly through interactions between stellar wind particles and the planet's upper atmosphere. The real excitement and focus of attention has been on TRAPPIST-1e, the planet that looks most like Earth in size and density and sits most comfortably in the middle of the habitable zone. When Webb studied TRAPPIST-1e, the initial data suggested that there might be signs of an atmosphere, though the results are still being analysed and have been the subject of vigorous scientific debate. Unlike planets B and C, which showed no atmosphere, Planet E appeared to show some absorption features in its spectrum that could indicate atmospheric gases. However, determining exactly which gases are present and in what amounts is challenging because the signals are subtle and could potentially be explained by other factors, like star spots on the host star or instrumental effects. If TRAPPIST-1e does have an atmosphere, the next crucial question is what it's made of. Is it a thick Venus-like blanket of carbon dioxide that would create a runaway greenhouse effect and make the surface uninhabitably hot? Is it a nitrogen-oxygen mix like Earth's that would support a temperate climate and potentially breathable air? Or is it something entirely different, a combination of gases we haven't seen before and don't have good intuitions about? Future Webb observations are planned to try to answer these questions by collecting more data with longer observation times and looking carefully for the spectral signatures of specific molecules like water vapor, oxygen, methane, and carbon dioxide. One fascinating aspect of the TRAPPIST-1 system that makes it unique among known planetary systems is that the planets are so close together that from the surface of one planet, you would see the others clearly in the sky, not just as points of light like planets in our solar system appear to us, but as actual visible disks that show apparent size and possibly even surface features. They wouldn't just be objects you need a telescope to see as anything other than dots. They would be prominent celestial objects visible to the naked eye. Some of the planets would appear larger in each other's skies than the Moon appears from Earth. If any of these worlds have atmospheres, you might even be able to see weather patterns on neighbouring planets with the naked eye or simple optics. Imagine standing on TRAPPIST-1f and looking up to see TRAPPIST-1e and TRAPPIST-1b, hanging in the sky as crescents, perhaps with visible clouds swirling in their atmospheres, or looking from TRAPPIST-1e toward TRAPPIST-1d and being able to see continents and oceans if they exist. The view from one of these planets would be spectacular and unlike anything we experience in our own solar system, where planets are small dim points in the sky. And if multiple planets in the system harbour life, you could imagine scenarios where biological signals from one world eventually reach and potentially influence another. Material ejected from one planet by asteroid impacts could carry microbes to other planets in the system, a process called panspermia. Given how close together the TRAPPIST-1 planets orbit, the transfer of material between planets would be much more efficient than in our solar system. Some scientists have speculated that if life arose on one TRAPPIST-1 planet, it might have spread to the others, meaning the system could host a common biosphere distributed across multiple worlds. The gravitational interactions between the 7 planets are incredibly complex and provide a wealth of information about the system. They're all pulling on each other as they orbit, creating subtle variations in their orbital periods and the exact timing of their transits across the star. These variations, called transit timing variations, have actually allowed scientists to determine the masses of the planets with remarkable precision by analysing how the gravitational tugs from neighbouring planets speed up or slow down each planet's orbit. The planets are locked in what's called orbital resonance, where the orbital periods are related by simple integer ratios. For every 2 orbits TRAPPIST-1c makes, TRAPPIST-1b makes almost exactly 3 orbits. For every 3 orbits TRAPPIST-1d makes, TRAPPIST-1c makes almost exactly 2 orbits. These resonances keep the system stable over billions of years and prevent the planets from eventually crashing into each other or being ejected from the system entirely. Climate models for the TRAPPIST-1 planets suggest a wide range of possible conditions depending on assumptions about atmospheric composition, cloud coverage, and other factors we can't yet measure directly. Some models indicate that planets in the habitable zone could have moderate temperatures and liquid water oceans, much like Earth. Other models suggest that the planets might have become tidally locked to their star very early in their history and developed extreme climate differences between their day and night sides, with the day side potentially too hot and the night side frozen solid. Some scenarios even suggest that water vapor from a warm day side could migrate to the cold night side, freeze out as ice, and eventually trap all the planet's water as a massive ice cap on the dark hemisphere, leaving the day side as a dry desert. The real conditions on these worlds might be different from anything our models predict, because we're extrapolating from our limited experience with Earth and our solar system into regimes we've never studied before. This is why direct observations with instruments like Webb are so crucial. We need data to constrain and validate our models. Every observation of a TRAPPIST-1 planet teaches us something new about how atmospheres behave, how climates evolve, and what factors determine habitability. The age of the TRAPPIST-1 system is still somewhat uncertain, but is estimated to be at least several billion years old, possibly as old as 8 billion years or more, significantly older than our 4.5 billion-year-old solar system. This means that if life did get started on any of these planets, it would have had even more time than life on Earth to evolve into complex forms. However, the frequent stellar flares from the red dwarf star might pose ongoing challenges for life. These flares could strip away atmospheres over time and bombard surfaces with harmful radiation, including ultraviolet light and high-energy particles. Any life on these worlds would need to adapt to these conditions, perhaps by living underground, underwater, where water provides radiation shielding, or by evolving robust DNA repair mechanisms to fix radiation damage. Alternatively, If the TRAPPIST-1 star is now in a calmer phase after an active youth, conditions might have recently become more favorable for life. In this scenario, any life on TRAPPIST-1 planets might be young, perhaps still at the microbial stage, which would make it harder to detect, but no less significant scientifically. The first detection of extraterrestrial life, even if it's just microbes, would be one of the most important discoveries in human history, fundamentally changing our understanding of biology and our place in the universe. The TRAPPIST-1 system has become one of the most intensively studied exoplanet systems, and it will remain a prime target for Webb observations for years to come. Each planet deserves multiple observations to characterize its atmosphere properly, and the data accumulated over several years will build a comprehensive picture of this remarkable system. Scientists hope to eventually determine whether any of the TRAPPIST-1 planets have retained thick atmospheres, what those atmospheres are made of, and whether conditions exist that could support life. The answers we find will inform our understanding of how common habitable planets are around ultra-cool dwarf stars, which make up a significant fraction of all stars in the galaxy. Chapter 5. Proxima Centauri b, our closest neighbouring world. Just over 4 light-years away, orbiting the closest star to our solar system, lies a planet that represents both our best hope and our greatest challenge in the search for habitable worlds. Proxima Centauri. B orbits in the habitable zone of Proxima Centauri, a red dwarf star that's part of the Alpha Centauri triple star system. While the James Webb Space Telescope faces some technical challenges in studying this planet due to the brightness of its nearby stellar companions, Alpha Centauri A and Alpha Centauri b, the proximity of this system makes it one of the most important targets in all of astronomy. At just 4.2 light-years away, Proxima Centauri b is the closest known exoplanet that might be habitable, and understanding whether it actually is habitable has profound implications for the search for life beyond Earth. Proxima Centauri b was discovered in 2016 using the radial velocity method, where astronomers detected the tiny wobble in the star's motion caused by the planet's gravity as the two orbit their common center of mass. The planet has a minimum mass about 1.3 times that of Earth, making it potentially rocky and Earth-like in composition, though we don't know its exact mass because the radial velocity method only gives a minimum value unless we know the inclination of the orbit. The planet orbits its star every 11.2 Earth days, staying well within the habitable zone where temperatures could theoretically allow liquid water to exist on the surface. Given how close it is to us in cosmic terms, you might think Proxima Centauri b would be easy to study and we'd already know everything about it. Unfortunately, reality is more complicated. The central challenge for Proxima Centauri b's habitability is the nature of its host star. Proxima Centauri is an active red dwarf that regularly produces powerful flares, some of which increase the star's brightness by 68% or more for brief periods, and send streams of charged particles and intense ultraviolet and X-ray radiation racing outward. These flares are far more energetic relative to the star's normal output than the largest solar flares our Sun produces. For a planet orbiting as close as Proxima Centauri b does, only about 5% of the distance from Earth to the Sun, these radiation doses could be devastating unless the planet has some form of protection. If Proxima Centauri b has a strong magnetic field generated by a liquid iron core, similar to Earth's magnetosphere, this field could deflect much of the charged particle radiation from stellar flares, just as Earth's magnetic field protects us from solar storms. The magnetic field would create a protective bubble around the planet that channels dangerous particles away from the atmosphere and toward the poles, where they create aurora displays but don't strip away the air. However, we don't know if the planet has such a magnetic field. Earth has one because our planet is large enough to maintain a hot liquid outer core where convective motions of electrically conducting iron generate magnetic fields through a process called the geodynamo. Proxima Centauri b might have a similar setup, or it might not, depending on its internal structure and thermal evolution. If Proxima Centauri b doesn't have a protective magnetic field, the repeated bombardment by stellar flares over billions of years could have stripped away any atmosphere the planet originally had, leaving behind a barren, airless rock much like Mercury in our solar system. Mercury has only an extremely thin exosphere rather than a proper atmosphere because it's too small to retain gases over geological time and too close to the Sun to escape atmospheric erosion by the solar wind. Proxima Centauri b faces similar challenges, but potentially even more severe ones given the activity level of its host star. This is why determining whether the planet has retained an atmosphere is the first crucial question that observations must answer. Recent Webb observations have focused on trying to detect any atmosphere around Proxima Centauri b by looking for absorption features during transits, though the viewing geometry makes this difficult. Unlike many exoplanets that transit directly in front of their stars from our perspective, Proxima Centauri b's orbit is not perfectly aligned, so transits are rare or possibly don't occur at all. This means astronomers have to use other techniques, like looking for the planet's thermal emission at infrared wavelengths, or trying to catch it at different phases as it orbits its star. These observations are challenging but not impossible, and they represent some of the most technically demanding work Webb can do. Even if Proxima Centauri b retained an atmosphere, the composition might be very different from Earth's due to the continuous input of energy from stellar flares. The flares drive complex atmospheric chemistry, potentially creating thick layers of ozone or other molecules that would shield the surface from ultraviolet radiation, but might also make the atmosphere chemically unusual. Alternatively, the flares might have dissociated water molecules in the atmosphere through photolysis, breaking H2O into hydrogen and oxygen. The light hydrogen atoms can escape to space while the heavier oxygen remains, potentially leading to an oxygen-rich atmosphere created through abiotic processes rather than biology. Such an oxygen-rich atmosphere might sound good because we breathe oxygen, but very high oxygen levels can actually be problematic for life because oxygen is so reactive it can damage biological molecules. There are also intriguing hints from observations that there might be a second planet in the Proxima Centauri system, dubbed Proxima Centauri c, orbiting further from the star where temperatures would be much colder. There are even suggestions of possible additional planets, or a debris disk of comets and asteroids similar to our solar system's Kuiper belt. If Proxima Centauri hosts a multi-planet system with gravitational interactions between the worlds, this could affect habitability in various ways. Gravitational perturbations from outer planets might stir up comets that occasionally impact the inner planets, delivering water and organic molecules. Or these interactions might destabilize orbits and make the system more chaotic over billions of years. The proximity of Proxima Centauri makes it potentially reachable with future technology in ways that more distant stars are not. While 4 light-years is still an enormous distance by any human standard, about 25 trillion miles or 40 trillion kilometers, it's close enough that some scientists have proposed sending tiny, ultra-fast probes powered by laser sails that could reach the system in just 20 to 30 years of flight time. Projects like Breakthrough Starshot are exploring the feasibility of such missions, which would involve building thousands of chip-sized spacecraft equipped with cameras and sensors, then accelerating them to about 20% of light speed using powerful ground-based laser arrays. At that velocity, the probes would reach Proxima Centauri in about 20 years and could transmit back close-up images and measurements of Proxima Centauri b. Such a mission faces enormous technical hurdles. The laser system would need to be incredibly powerful. The tiny spacecraft would need to survive acceleration to 60 million meters per second. They'd need to survive impacts with interstellar dust particles that at such speeds hit with the force of bombs, and they'd need to transmit data back across 4 light years with incredibly weak signals. But unlike interstellar missions with conventional propulsion that would take tens of thousands of years, a laser sail mission to Proxima Centauri could potentially be accomplished within a human lifetime. If we launch such a mission today, we might receive the first images back in about 2070, within the lifespan of children born this year. Webb's observations of the broader Alpha Centauri system have already produced exciting results. In 2025, Webb found strong evidence of a giant planet orbiting Alpha Centauri A, the Sun-like star in the system. While this planet wouldn't be in the habitable zone because it orbits too far from the star at about twice the Earth-Sun distance, its discovery suggests that the Alpha Centauri system might host multiple planets at various distances from their stars. The possibility of additional, as yet undiscovered planets in the habitable zones of Alpha Centauri A or B is tantalizing and motivates further searches. From the perspective of studying planetary habitability and the search for life, Proxima Centauri b represents a crucial test case whose importance extends far beyond this single planet. If life can survive and thrive on a planet orbiting an active red dwarf star despite the flares and radiation, then habitable worlds might be extraordinarily common in the universe because red dwarfs make up about 75% of all stars in the galaxy. There are probably 150 billion red dwarf stars in the Milky Way alone. If even a small percentage of them host habitable planets, that's billions of potential homes for life just in our galaxy. On the other hand, if the stellar activity of red dwarfs proves too harsh for life, if planets like Proxima Centauri b lose their atmospheres or suffer such intense radiation that life can't gain a foothold, then we might need to focus our search on more sun-like stars, which are less common but potentially offer more stable and benign conditions for life to develop and evolve. Sun-like stars make up only about 7% of all stars, so this would dramatically reduce the number of potential habitable worlds. Understanding whether Proxima Centauri b is habitable or sterile will help us answer this fundamental question about where life can exist in the universe. Chapter 6. New Worlds Revealed by Webb in 2025. The year 2025 has been particularly productive for exoplanet discoveries with the James Webb Space Telescope, with several remarkable findings that expand our understanding of planetary diversity and the search for habitable worlds. Among the most exciting discoveries is TWA 7b, which represents Webb's first directly imaged exoplanet discovery and demonstrates new capabilities for finding and studying young planets still in the process of forming. TWA 7b orbits a young star in the TW Hydrae Association, a group of stars that are only about 10 million years old, mere infants in cosmic terms. What makes this discovery particularly significant is that the planet is about 10 times less massive than previously imaged exoplanets, with a mass similar to Saturn at roughly 30% of Jupiter's mass. The planet was discovered sitting within a narrow ring in a debris disk surrounding its star, exactly where theoretical models predicted a planet should be if it was gravitationally clearing a gap in the disk material. This discovery validates our theories of planet formation and demonstrates that Webb can detect planets that are significantly smaller and lighter than what previous direct imaging could achieve. The discovery was made possible by a French-designed coronagraph installed on Webb's MIRI instrument, which works by blocking the light from the star, similar to how a solar eclipse blocks the sun's light, allowing much fainter nearby objects like planets to be seen. This coronagraph represents a major technological achievement and opens the door to directly imaging Earth-sized planets around nearby stars in the future. The ability to take actual pictures of exoplanets rather than just inferring their existence from indirect effects is transformative because direct images can reveal information about planet atmospheres, cloud patterns, surface features, and even seasonal changes as planets orbit their stars. Another remarkable 2025 discovery involves free-floating planets, rogue worlds that don't orbit any star but instead drift alone through interstellar space. Webb observations revealed that some of these free-floating planetary mass objects, with masses between 5 and 10 times that of Jupiter, have their own circumplanetary disks of gas and dust surrounding them. Even more astonishing, these disks show signs of silicate grains crystallizing, which is the first step toward forming rocky planets or moons. This means that lonely rogue planets drifting through space might be able to build their own mini-planetary systems, with rocky worlds or moons forming around them despite the absence of a star. This finding challenges our understanding of where and how planets can form. We thought planetary systems required stars at their centers to provide the energy and gravitational structure for planet formation. But these observations suggest that giant planets can host their own planet-forming disks and potentially grow families of smaller worlds orbiting them. If this process is common, it would mean there might be rocky Earth-sized worlds orbiting rogue planets throughout the galaxy. Worlds that never see a sunrise because they have no sun, but that might still be warm enough for liquid water if tidal heating or radioactive decay provides enough warmth. Webb has also made significant advances in studying atmospheric escape, the process by which planets lose their atmospheres to space over time. In December 2025, Webb observed WASP-107b, a giant puffy exoplanet often called a superpuff, or cotton candy planet, because its density is extremely low, like cotton candy. Webb detected a massive cloud of helium gas escaping from this planet's atmosphere, with the escaping gas extending nearly 10 times the planet's radius and actually preceding the planet along its orbital path. This is the first time the James Webb Space Telescope has observed atmospheric escape on this scale, and the observations provide crucial data for understanding how and why some planets lose their atmospheres while others retain them. Understanding atmospheric escape is critical for determining which planets can remain habitable over billions of years. If a planet loses its atmosphere too quickly, any life that might have started there would be extinguished as the air disappears and liquid water boils away into space. The observations of WASP-107b show us the extreme end of atmospheric escape, but similar processes at lower rates affect all planets to some degree. By studying atmospheric escape on different planets under different conditions, scientists can develop better models for predicting which planets will retain breathable atmospheres over geological time. Webb observations in 2025 have also continued to refine our understanding of K2-18b's atmosphere. Follow-up observations with longer integration times have provided higher quality spectra that allow more precise identification of atmospheric molecules. The debate over whether dimethyl sulfide is really present in the atmosphere continues, with some scientists arguing that the spectral features could be explained by other molecules or combinations of molecules. This scientific back and forth is normal and healthy, representing the careful, methodical approach that's necessary when making claims as significant as detecting potential biosignatures on other worlds. Other 2025 Webb observations have targeted hot Jupiters to study their extreme atmospheric chemistry. These gas giants orbiting very close to their stars have day-side temperatures reaching 2000 degrees Celsius or higher, hot enough that rocks would melt and metals would vaporize. Webb's infrared observations can detect molecules like titanium oxide, vanadium oxide, and even vaporized iron in these extreme atmospheres. While hot Jupiters aren't candidates for habitability, studying their atmospheres teaches us about atmospheric chemistry under extreme conditions and helps us develop better models and analysis techniques that can be applied to more temperate worlds. Chapter 7: The science behind biosignatures and the search for life. The ultimate goal of studying exoplanets with the James Webb Space Telescope isn't just to catalogue worlds or understand planetary formation, though those are important scientific objectives in their own right. The real prize, the discovery that would transform humanity's understanding of our place in the universe, is to find definitive evidence of life beyond Earth. Webb is equipped with the tools to detect the chemical fingerprints that life leaves behind, and understanding how scientists search for biosignatures and what makes a particular molecule a potential sign of life is crucial to appreciating just how revolutionary these discoveries are and how close we might be to answering the ancient question of whether we're alone. On Earth, life has fundamentally altered our planet's atmosphere over billions of years in ways that would be impossible without biology. The oxygen we breathe makes up about 21% of our atmosphere, and almost all of it comes from photosynthetic organisms, including plants, algae, and cyanobacteria. Oxygen is highly reactive chemically, meaning it combines readily with other elements and compounds. Without life constantly producing oxygen through photosynthesis, the oxygen in our atmosphere would react with rocks through weathering, with dissolved iron in the oceans causing rust, with volcanic gases like hydrogen sulfide and carbon monoxide, and with organic molecules produced by non-biological processes. All the oxygen would be gone within a few million years, which is geologically very rapid, just a blink of an eye in the 4.5 billion year history of our planet. This makes oxygen a powerful potential biosignature when detected in the right context. If you find a planet with significant amounts of molecular oxygen in its atmosphere, especially in combination with other gases like methane that react with oxygen, it strongly suggests that something biological is happening to continuously produce and maintain these gases in chemical disequilibrium. However, oxygen alone isn't a slam dunk biosignature because there are some abiotic processes that can produce atmospheric oxygen without biology. The most important is photolysis of water vapor by ultraviolet light from the star, which splits water molecules into hydrogen and oxygen. The light hydrogen can escape to space, while the heavier oxygen accumulates in the atmosphere. Scientists have calculated how much oxygen photolysis can produce under various conditions, and if a planet has oxygen levels significantly exceeding these abiotic predictions, biology becomes a much more attractive explanation. The key is finding oxygen in the right amounts, and in combination with other gases that create a strong case for biological activity rather than just chemistry and physics. This is why discovering multiple biosignature gases simultaneously would be much more convincing than finding any single gas in isolation. Methane is another key molecule in the biosignature toolkit. On Earth, vast quantities of methane are produced by microorganisms in wetlands, in the digestive systems of ruminant animals like cows, in rice paddies, in termite mounds, and in various other environments where organic matter decays in the absence of oxygen. These methanogenic microbes are among the most ancient forms of life on Earth, using a metabolism that predates oxygen-producing photosynthesis. Methane can also be produced by geological processes, including volcanic activity and reactions between water and certain types of rocks, so detecting methane alone doesn't prove biology. But when methane appears, alongside oxygen or other gases in certain combinations, it becomes more likely that life is involved because maintaining high levels of both gases simultaneously requires continuous production to overcome their tendency to react together. Dimethyl sulfide, or DMS, is one of the most promising biosignatures precisely because we don't know of any significant non-biological sources for this molecule in planetary atmospheres. On Earth, DMS is produced primarily by ocean-dwelling phytoplankton, microscopic photosynthetic organisms that live in the sunlit surface layers of the ocean. These organisms produce DMS as they break down a sulfur-containing compound called DMSP, and the DMS then escapes from the ocean into the atmosphere where it plays a role in cloud formation. In fact, DMS is responsible for much of what we think of as the distinctive smell of the ocean. The potential detection of DMS on K2-18b created such excitement precisely because it's so hard to explain without biology. Unlike oxygen or methane, which have known abiotic production mechanisms, DMS in large quantities really seems to require life. However, the detection remains tentative and controversial. The spectral features that might indicate DMS could potentially be caused by other molecules or combinations of molecules, or they might be artifacts of the way light interacts with clouds or hazes in the planet's atmosphere. Confirming the presence of DMS requires additional observations with higher signal-to-noise ratios and careful analysis to rule out alternative explanations. The scientific community is appropriately cautious because the stakes are so high. Phosphine is another gas that recently gained attention as a potential biosignature when it was controversially detected in Venus's atmosphere in 2020, though that detection has since been disputed and remains unconfirmed. On Earth, phosphine is produced by some microbes living in oxygen-poor environments. The molecule is highly reactive and quickly breaks down in the presence of oxygen or when exposed to ultraviolet light, so finding it in an atmosphere suggests there must be a continuous source producing it faster than it's destroyed. The Venus phosphine claim sparked intense scientific debate about what non-biological processes might produce phosphine and what detection standards should be required before claiming a biosignature discovery. This debate has been healthy for the field, forcing scientists to think more carefully about how to distinguish biological from non-biological sources. Beyond individual molecules, scientists also look for combinations of gases that wouldn't persist together in thermodynamic equilibrium unless something was actively maintaining them. This concept of chemical disequilibrium is powerful because it's based on fundamental principles of chemistry rather than our specific knowledge of Earth's biochemistry. On a lifeless planet, atmospheric chemistry tends toward equilibrium where reactions have proceeded as far as they can go, given the available energy and the temperature and pressure conditions. But life drives chemistry away from equilibrium by using energy to build complex molecules, and by producing waste products that wouldn't accumulate without biology. For example, finding both methane and oxygen together in significant quantities is interesting precisely because these gases react with each other. The reaction between methane and oxygen produces carbon dioxide and water, and it proceeds spontaneously given enough time or with a spark to start it. On a lifeless planet, you might find methane in a reducing atmosphere without oxygen, or you might find oxygen in an oxidizing atmosphere without methane. But having both simultaneously at high levels requires that something is continuously producing both gases faster than they can react away. On Earth, that something is life, with methanogens producing methane and photosynthetic organisms producing oxygen. The spectroscopic techniques Webb uses to detect these molecules are incredibly sophisticated, but also subject to various sources of error ambiguity, and systematic uncertainties. When Webb observes a planet transiting in front of its star, the telescope is detecting tiny changes in the starlight, changes measured in parts per million or even parts per billion. A planet like Earth transiting in front of a Sun-like star blocks about 0.01% of the star's light, and the additional absorption by atmospheric molecules is a tiny fraction of that tiny amount. Extracting the planetary atmospheric signal from the stellar light requires careful calibration, sophisticated data analysis pipelines, and complex computer models. Different molecules can have overlapping spectral features where they absorb light at similar wavelengths, making it challenging to determine exactly which gases are present and in what amounts. Water vapor, methane, and ammonia all have absorption features in some of the same wavelength ranges, so distinguishing between them requires high-resolution spectra and careful modelling. Scientists must consider multiple possible explanations for any given spectrum and use statistical methods to determine which interpretation is most likely given the data. This often means that initial detections are tentative and require follow-up observations to confirm or refute. One of the biggest challenges in biosignature detection is that we're searching based primarily on what we know about life on Earth. But alien life might be very different. Life on other worlds might use different biochemistry, might produce different metabolic waste products, might require different environmental conditions, and might leave different fingerprints on its planet's atmosphere. Some scientists advocate for a more general approach, looking for any signs of complex chemistry that's hard to explain with simple physical and chemical processes alone. If you find an atmosphere with a dozen different molecules present in specific ratios that don't make thermodynamic sense for abiotic chemistry, that might be a sign that something interesting and potentially biological is happening, even if none of the individual molecules is a classic biosignature by Earth standards. False positives are a major concern that keeps scientists cautious and conservative in their interpretations. We absolutely do not want to announce the discovery of life on another world, only to later realize we were fooled by some unusual geological process, by clouds or hazes mimicking the spectral signature of biosignature molecules, by instrumental artifacts, or by incorrect data analysis. The discovery of extraterrestrial life would be one of the most important findings in human history, certainly the most important in biology, and arguably the most important in all of science. The standards of evidence must therefore be exceptionally and appropriately high. This is why any claimed biosignature detection requires extensive follow-up observations from multiple independent teams using different instruments and analysis methods, peer review by skeptical scientists looking for alternative explanations, and probably confirmations from multiple telescopes before the scientific community would reach consensus. Webb's observations are giving us the data we need to search for biosignatures with unprecedented sensitivity and precision, but confirming any detection of life will require multiple independent lines of evidence, probably observations of multiple biosignature gases simultaneously, and likely years of additional study before we can say with confidence that we've found life beyond Earth. Chapter 8. What makes a planet better than Earth? Throughout this documentary, we've explored multiple planets that scientists consider potentially habitable and possibly even better suited for life than Earth in certain ways. But what does it actually mean for a planet to be better than Earth? What characteristics would make an alien world not just habitable, but actually superior as a home for life? Understanding what factors contribute to habitability and long-term stability helps us appreciate both how special Earth is and how the universe might offer other worlds with different advantages. One way a planet could be better than Earth is by orbiting a more stable, longer-lived star. Our Sun is a G-type yellow dwarf star with a total lifespan of about 10 billion years, of which about 4.6 billion have already passed. In another 5 billion years or so, the Sun will exhaust its hydrogen fuel and begin expanding into a red giant, eventually engulfing Mercury, Venus, and quite possibly Earth. But long before that final catastrophe, the gradually increasing luminosity of the aging Sun will make Earth uninhabitable. In about 1 billion years, maybe 1.5 billion at most, the Sun will be bright enough that Earth's oceans will evaporate, creating a runaway greenhouse effect that turns our planet into a second Venus. Planets orbiting smaller, cooler, more stable red dwarf stars could have much longer windows of habitability. The smallest red dwarfs will burn their hydrogen fuel for trillions of years, far longer than the current 13.8 billion year age of the universe. A habitable planet around such a star would have almost unlimited time for life to evolve, develop complexity, and perhaps eventually give rise to intelligence and civilization. If the evolution of complex life requires billions of years as it did on Earth, then planets around red dwarfs have hundreds or even thousands of times as long for these processes to unfold. By the time the universe is 100 billion or a trillion years old and most stars have burned out, planets around red dwarfs might host civilizations billions of years more advanced than ours. Another advantage some exoplanets might have is a larger size and stronger gravity that helps them retain their atmospheres over billions of years. Earth has lost some atmosphere to space over its history, particularly light elements like hydrogen and helium that can escape Earth's relatively weak gravitational pull. Mars, being smaller with weaker gravity, lost most of its atmosphere early in its history and transformed from a warm, wet world with rivers and possibly oceans into the cold, dry desert we see today. A super-Earth with twice Earth's mass would have escape velocity high enough that atmospheric loss to space would be negligible even in the face of intense stellar activity. Such a planet could maintain a thick protective atmosphere essentially forever, providing stable conditions for life over extremely long timescales. Some planets might have more optimal locations within their system's habitable zone compared to Earth. While Earth sits comfortably in the habitable zone, we're actually somewhat close to the inner edge where the greenhouse effect could potentially run away given the wrong conditions. Venus, our neighbour, shows how catastrophically wrong things can go. A planet located in the middle of a wider habitable zone would have more margin for error, more room for atmospheric evolution without slipping into runaway greenhouse or snowball states. Such a planet would be inherently more stable against climatic fluctuations. Water availability is another factor where some exoplanets might excel compared to Earth. Earth's surface is about 71% ocean, which seems like a lot until you consider that all of Earth's water, if gathered into a sphere, would be only about 1,400 kilometers in diameter, tiny compared to Earth's 12,700 kilometer diameter. Earth is actually a relatively dry planet. Some exoplanets might have vastly more water, perhaps delivered by countless comet impacts during formation or inherited from ice-rich regions of their protoplanetary disks. An ocean world with global seas hundreds of kilometers deep would have enormous buffering capacity against climate change, as water has very high heat capacity and the oceans would moderate temperature swings. Of course, too much water might actually be a problem. If a planet is completely covered in deep oceans with no land at all, this could limit the types of ecosystems that develop. On Earth, some of the most productive ecosystems are in coastal regions where land and sea meet, where nutrients wash from land into the ocean, and where complex food webs develop. A world with no continents might support microbial life and simple ocean-dwelling organisms, but might face challenges developing the kind of complex land-based ecosystems that eventually gave rise to intelligence on Earth. The optimal amount of water might be somewhat more than Earth has, enough for extensive oceans and seas, but still with substantial land masses. Chemical abundance is another area where some planets might have advantages. Earth formed in a region of the solar system with particular abundances of different elements, giving us specific amounts of carbon, nitrogen, oxygen, phosphorus, sulfur, and various metals. But different stars have different compositions depending on when and where they formed in galactic history, and planets around those stars inherit those compositions. A planet slightly richer in certain biologically important elements might support more abundant and diverse life than Earth does. Phosphorus in particular is thought to be a potentially limiting nutrient for life, and a planet with more abundant phosphorus might support larger biospheres. Magnetic field strength is crucial for long-term habitability because the magnetic field shields the planet from stellar wind particles that would otherwise erode the atmosphere. Earth's magnetic field is generated by convection of liquid iron in the outer core, and its strength depends on the size and temperature of the core and the rate of convection. A larger planet with a bigger iron core or faster internal convection might generate a stronger magnetic field than Earth's, providing better protection against atmospheric erosion and allowing the planet to retain its atmosphere even around very active stars. Some exoplanets might have magnetic fields 10 times stronger than Earth's, creating enormous protective magnetospheres. Plate tectonics, the process by which Earth's outer shell is broken into plates that move around over geological time, plays a crucial role in regulating Earth's climate and recycling nutrients. Plate tectonics helps regulate carbon dioxide levels in the atmosphere through the carbonate-silicate cycle, where CO2 dissolved in rain forms carbonic acid that weathers rocks. The weathering products wash into the ocean, marine organisms incorporate them into shells, and eventually the carbonates get subducted back into the mantle at plate boundaries and return to the atmosphere through volcanic eruptions. This cycle acts as a thermostat, increasing weathering rates when the planet is warm and decreasing them when it's cold, stabilizing the climate over hundreds of millions of years. A planet with more active plate tectonics than Earth might have even better climate regulation. More rapid plate motion would speed up the carbonate-silicate cycle, allowing faster responses to climate perturbations. More volcanic activity would provide more outgassing to replenish atmospheric volatiles and more heat flux from the interior. The increased tectonic activity might also create more diverse geological environments and ecological niches, potentially supporting greater biological diversity. Of course, too much volcanic activity could also be problematic, creating an atmosphere too thick with volcanic gases or causing frequent catastrophic eruptions that disrupt ecosystems. Orbital stability is another factor where some exoplanets might have advantages. Earth's orbit is fairly stable thanks to Jupiter's presence in the outer solar system. Jupiter's enormous mass helps clear out asteroids and comets that might otherwise bombard the inner solar system, and its gravitational influence helps stabilize the orbits of the inner planets. A planetary system with an even better arranged architecture of giant planets might provide even more stability for its inner rocky worlds. Or a planet in a system with fewer giant planets might avoid gravitational perturbations entirely, though it might receive more comet impacts. Some scientists have even speculated about whether a tidally locked planet, where one side always faces its star while the other faces into eternal night, might actually provide better conditions for life than a rotating planet like Earth. A tidally locked world in the habitable zone would have extreme temperature differences between day and night sides, but the twilight ring between them might offer optimal conditions. The day side would provide constant sunlight for photosynthesis without the day-night cycles that limit productivity on Earth. The night side would act as a heat sink, helping to regulate global temperatures. And the twilight zone would offer moderate temperatures and interesting lighting conditions with the star perpetually on the horizon. Moon systems might also make some planets better than Earth. While Earth has one relatively large moon that creates tides and stabilizes Earth's axial tilt, preventing dramatic climate variations, some exoplanets might have multiple large moons, providing even stronger tidal mixing of oceans and more complex and interesting tidal patterns. Or a planet might be a moon itself, orbiting a giant planet in the habitable zone and receiving heat from both stellar radiation and tidal heating from the giant planet's gravity. Such a moon planet might have extremely stable conditions and multiple energy sources for life. Finally, a planet that formed later in cosmic history than Earth might have better conditions for life simply because later forming planetary systems inherit higher abundances of heavy elements from previous generations of stars. The first stars in the universe contained only hydrogen and helium because those were the only elements created in the Big Bang. All heavier elements, carbon, oxygen, nitrogen, iron, and everything else, were created in the cores of stars through nuclear fusion and dispersed into space when those stars exploded as supernovae. Each generation of stars enriches the cosmos with more heavy elements. Planets forming today have access to more carbon, nitrogen, oxygen, and metals than Earth had when it formed 4.5 billion years ago, potentially making them richer in the elements needed for life. All these factors suggest that while Earth is an excellent planet for life and wonderfully suited for human existence, there might be planets out there that are even better in certain ways. They might orbit longer-lived stars, giving life more time to evolve. They might have stronger magnetic fields, better protecting their atmospheres. They might have more water, more optimal chemical abundances, more active plate tectonics, or other advantages we haven't even considered. Finding and studying these worlds will teach us what factors matter most for habitability and might even point toward places where life is more likely and more abundant than on Earth. That's what makes the search so exciting. We're not just looking for copies of Earth, we're looking for the full range of habitable worlds the universe has to offer. Chapter 9. The Future of Exoplanet Exploration. The discoveries being made by the James Webb Space Telescope represent just the beginning of what promises to be a golden age of exoplanet science. Each new observation adds to our knowledge, refines our theories, and raises new questions that will drive research for decades to come. The implications of these discoveries extend far beyond astronomy, touching on biology, geology, chemistry, and philosophy. They force us to reconsider our place in the universe and our understanding of how common or rare life might be. Looking ahead, the next decade will see remarkable advances in our ability to find and study potentially habitable worlds. The James Webb Space Telescope itself will continue operating for at least another 15 years, probably longer if all goes well, giving scientists an extended window to study the most promising exoplanets in unprecedented detail. Each additional year of observations will build up larger data sets for key targets like K2-18b, LHS 1140b, and the TRAPPIST-1 planets. With more data comes better signal-to-noise ratios, more precise molecular detections, and the ability to track changes over time. Scientists will observe these worlds through multiple orbits and potentially multiple years, looking for seasonal variations, weather patterns, and long-term atmospheric evolution. future Webb observation programs will systematically survey potentially habitable planets around nearby stars, building up a comprehensive census of atmospheric compositions and surface conditions. This survey approach will reveal patterns and correlations that aren't obvious from studying individual planets in isolation. We might find that planets above a certain size always have hydrogen atmospheres, or that planets around certain types of stars tend to lose their atmospheres more readily. These statistical insights will guide our understanding of planet formation and evolution and help us predict which types of systems are most likely to host habitable worlds. But Webb is just one telescope, and the next generation of observatories will build on its foundation with even more powerful capabilities. On the ground, 3 enormous telescopes, collectively called the Extremely Large Telescopes, are under construction or in planning. The Extremely Large Telescope in Chile will have a primary mirror 39 meters across, dwarfing even the largest existing telescopes and providing collecting area equivalent to thousands of WeBs. The 30-meter telescope planned for Hawaii and the Giant Magellan Telescope, also in Chile, will have mirrors 30 and 25 meters in effective diameter respectively. These ground-based giants will be able to take direct images of some larger exoplanets and study atmospheric properties in wavelengths where Earth's atmosphere is relatively transparent. Ground-based telescopes face challenges that space telescopes don't, primarily Earth's atmosphere, which absorbs much of the infrared light that's so useful for exoplanet studies. However, modern adaptive optic systems can correct for atmospheric turbulence in real time, and the sheer light-gathering power of these enormous mirrors provides advantages that offset some atmospheric limitations. Ground telescopes are also easier to upgrade and maintain than space telescopes, allowing them to incorporate new instruments and technologies as they become available. The combination of space-based and ground-based observations, each with their own strengths, will provide a more complete picture than either could alone. In space, several new missions are planned specifically for exoplanet characterization. The Habitable Worlds Observatory, currently in early planning stages, would be a large space telescope optimized for finding and characterizing Earth-like planets around Sun-like stars, something that remains challenging even for Webb. This mission would use advanced coronagraphs to block starlight and directly image rocky planets in habitable zones, taking spectra that could reveal biosignatures. The technology requirements are extremely demanding, but if successful, the Habitable Worlds Observatory could provide definitive answers about habitability and potential life on dozens of nearby Earth-like worlds. The European Space Agency's Ariel mission, scheduled to launch in 2029, will survey the atmospheres of about 1,000 known exoplanets, providing a comprehensive picture of atmospheric chemistry across a wide range of planet types. While Ariel won't be optimized for finding biosignatures on Earth-like planets, its systematic survey approach will reveal how atmospheric composition varies with planet size, orbital distance, stellar type, and other parameters. This statistical understanding is crucial for developing comprehensive theories of planetary atmospheres and for identifying which planets deserve follow-up study with more powerful telescopes. Technological advances in telescope design, detector sensitivity, and data analysis methods will enable discoveries we can barely imagine today. Machine learning and artificial intelligence are already being applied to exoplanet data, helping identify faint signals that human analysts might miss, and automating the tedious work of processing millions of spectra. Future AI systems might be able to recognize patterns in atmospheric spectra that indicate biological activity, even when the patterns don't match our preconceived notions of what biosignatures should look like. These algorithms could help us avoid the anthropocentric bias of assuming alien life will exactly resemble Earth life. Direct spectroscopy of Earth-sized planets around Sun-like stars remains a major challenge because these planets are so small and so close to their much brighter stars that separating the planetary signal from the stellar glare is extraordinarily difficult. Future mission concepts propose various innovative solutions. Starshade missions would fly a large opaque disk on a separate spacecraft positioned precisely between a telescope and the target star system, blocking the starlight and creating an artificial eclipse that makes planets visible. Extremely large telescopes with advanced adaptive optics and coronagraphs might achieve the contrast ratios needed to directly image Earth twins. Interferometry, combining light from multiple telescopes, might provide the angular resolution needed to separate planets from their stars, even for relatively nearby systems. The search for biosignatures will expand beyond atmospheric chemistry to include other potential indicators of life. Vegetation on Earth has a characteristic reflectance spectrum with a sharp increase in reflectivity at near-infrared wavelengths due to the cellular structure of leaves, an effect called the vegetation red edge. If alien plants have similar pigments and structures, future telescopes might detect this spectral signature in the reflected light from exoplanets, providing evidence of photosynthetic life even without atmospheric biosignatures. Other possibilities include detecting the glint of sunlight reflecting off lakes or oceans on a planet's surface, looking for regular patterns in a planet's rotation that might indicate artificial structures, or searching for industrial pollutants in atmospheres that might indicate technological civilizations. The search for technosignatures, signs of technology rather than just biology, is gaining scientific legitimacy and funding after being marginalized for decades. While SETI has traditionally focused on searching for radio signals from alien civilizations, the new generation of technosignature research considers a much broader range of possible indicators, including laser pulses, atmospheric pollutants from industry, infrared signatures from Dyson spheres or other megastructures, unusual transits indicating large artificial objects, and modifications to planetary surfaces visible in direct images. Webb and other telescopes could potentially detect some of these signatures if they exist, though finding them would require knowing what to look for. Interstellar probe missions, while still in the conceptual phase and facing enormous technical challenges, might become reality within the next few decades. The Breakthrough Starshot initiative is exploring the feasibility of laser-propelled nanosatellites that could reach nearby stars like Proxima Centauri in 20 to 30 years. Such probes would be tiny, perhaps just centimeters across, but equipped with cameras and sensors that could take close-up images of exoplanets and transmit data back to Earth. Even with significant technical hurdles, including the enormous laser power requirements, surviving acceleration, protection from interstellar dust, and maintaining communication across light years, such missions represent a potential path to studying exoplanets up close rather than from afar. International collaboration will be crucial for maximizing scientific return from these missions and ensuring that the discoveries benefit all humanity rather than individual nations. The James Webb Space Telescope itself is a partnership between NASA, the European Space Agency, and the Canadian Space Agency, with contributions from thousands of scientists and engineers worldwide. Future missions will likely involve even broader international cooperation as costs increase and the technical challenges grow. Sharing data openly and encouraging participation from scientists worldwide ensures that the best ideas and most talented people contribute regardless of their country of origin. Public engagement and education will play vital roles in maintaining support for these long-term, expensive research programs. The images and discoveries from Webb have captured public imagination in ways that abstract scientific papers cannot, reminding people why space exploration matters and what we stand to gain from studying the universe. As the discoveries continue and potentially culminate in the detection of life beyond Earth, public interest will likely intensify. Scientists and communicators must work to help people understand not just what we're finding, but why it matters and how it changes our perspective on existence. The economic and technological spin-offs from exoplanet research extend far beyond astronomy. The detector technologies developed for studying faint exoplanet atmospheres find applications in medical imaging, environmental monitoring, and materials science. The data analysis techniques for extracting weak signals from noisy data are relevant to fields from finance to genomics. The precision optics required for coronagraphs and adaptive optics systems advance capabilities in microscopy and manufacturing. The computational methods for modeling planetary atmospheres improve weather forecasting and climate models for Earth. Investment in fundamental research consistently produces unexpected benefits across many domains, often in ways that weren't foreseeable when the research began. Looking decades into the future, we can imagine a time when we not only know whether life exists on other worlds, but have catalogued potentially habitable planets across hundreds of light years, understand the conditions under which life emerges and evolves, and perhaps have even detected signs of intelligence beyond Earth. The generation of scientists born today will grow up in a world where potentially habitable exoplanets are as familiar as the planets in our own solar system are to us. They'll be able to study entire populations of Earth-like worlds statistically, understanding habitability not from a sample size of one, but from hundreds or thousands of examples. The insights gained will transform our understanding of life, its origins, its requirements, and its frequency in the universe. Final chapter: a universe transformed by discovery. We stand at a unique and extraordinary moment in human history. For the first time ever, we have the technology to detect potentially habitable planets around other stars, to analyze their atmospheres in detail, and to search for signs of life beyond Earth. What was pure speculation just decades ago, the stuff of science fiction and philosophical musing, has become observational science. We're no longer wondering whether other Earth-like worlds exist. We know they do. The question now is which of them host life, and how common or rare that life might be. The James Webb Space Telescope has revealed a universe far richer, more diverse, and more promising than we dared imagine. The planets we've discovered aren't just copies of Earth scattered across the galaxy. They're genuinely alien worlds with characteristics we never anticipated, environments we couldn't have predicted, and possibilities we're still learning to comprehend. K2-18b might be a global ocean world with possible biosignatures floating in its atmosphere. LHS 1140b might have an Earth-like atmosphere with nitrogen and oxygen. The TRAPPIST-1 system offers 7 Earth-sized worlds, like a natural laboratory for studying habitability. Proxima Centauri b orbits the closest star to our Sun, potentially reachable with future technology. Each of these worlds represents a different answer to the question of what makes a planet habitable. Some have deep oceans, others might have continents and seas like Earth, still others might be entirely ice-covered with subsurface oceans. Some orbit rapidly around small red dwarfs, while others have longer orbits around more sun-like stars. Some are larger than Earth with stronger gravity, others are more similar in size. The diversity is staggering, and it teaches us that habitability isn't a single narrow set of conditions, but rather a broad range of possibilities that the universe explores through countless variations. The tentative detection of dimethyl sulfide on K2-18b if confirmed, could be our first identification of a biosignature gas produced by life on another world. Even if this particular detection turns out to be incorrect, the fact that we can search for such molecules and potentially find them means the discovery of extraterrestrial life might be just years or decades away rather than centuries. We might be the generation that finally answers the age-old question of whether we're alone. That possibility is both thrilling and humbling. Whatever we ultimately find, the search itself is transforming humanity. We're learning that our planet, while perhaps not unique in the universe, is certainly extraordinary. The specific combination of factors that make Earth habitable, from our position in the habitable zone to our large stabilizing moon, from our active plate tectonics to our protective magnetic field, from our atmospheric composition to our abundant liquid water, represents a fortunate convergence of circumstances that took billions of years to establish. Other planets might match or exceed Earth in some characteristics, but finding another world that's as perfectly suited to human life as our home planet will likely prove difficult. This realization should inspire us to take better care of Earth. We've found thousands of exoplanets, but we haven't found another world we could simply move to if we destroy this one. Earth's habitability isn't guaranteed forever. We face challenges from climate change, habitat destruction, pollution, and resource depletion that could dramatically alter our planet's ability to support not just human civilization, but the rich tapestry of life that took billions of years to evolve. The perspective gained from studying exoplanets, seeing both the common and the rare aspects of planetary habitability, underscores how precious Earth is. At the same time, knowing that potentially habitable worlds exist and might be reachable, with far future technology provides hope for humanity's long-term future. Earth will not remain habitable forever. In about 1 billion years, the gradually brightening sun will make our planet too hot for life. In 5 billion years, the sun will expand into a red giant and possibly engulf Earth entirely. These timescales are so vast they're difficult to comprehend, but they're finite. If humanity survives and continues advancing technologically for millions of years, having other potentially habitable worlds as destinations might be crucial for our species' ultimate survival. The discoveries from Webb and future telescopes will also inform our understanding of our own planet's past and future. By studying how atmospheres evolve on worlds with different masses, different stellar environments, and different initial compositions, we learn about the processes that shaped Earth's atmosphere over billions of years. We can better understand how Earth might change in the future as the sun slowly brightens, and how human activities might push our climate outside its historical range. The study of exoplanets is in many ways the study of Earth writ large, examining all the ways rocky planets can evolve and all the factors that determine their long-term habitability. The philosophical implications of finding life beyond Earth, should that discovery occur, would be profound and transformative. It would tell us that the emergence of life from non-living chemistry is not a unique miracle, but a natural consequence of physics and chemistry under the right conditions. It would suggest that the universe might be teeming with life, possibly including intelligent civilizations far older and more advanced than ours. It would force us to reconsider questions about life's purpose, humanity's significance, and our relationship to the cosmos. These are questions that have preoccupied philosophers and theologians for millennia, and we might finally have empirical data to inform the discussions. Even if we search for decades and find no signs of life, that result would also be scientifically valuable and philosophically significant. It would suggest that something about life's origin or its survival is more difficult or rare than current theories predict. It might indicate that while simple microbial life is common, complex multicellular life is rare, or that while primitive life is abundant, the evolution of intelligence is extraordinarily unlikely. These findings would reshape our understanding of biology and evolution and would make us appreciate even more how special and improbable our existence might be. The technologies being developed to study exoplanets, from adaptive optics to coronagraphs to ultrasensitive infrared detectors, represent some of humanity's most impressive engineering achievements. The ability to detect the chemical composition of a planet's atmosphere from hundreds of light years away by analysing subtle features in starlight to distinguish between biological and non-biological sources of gases and to model complex atmospheric chemistry and dynamics showcases the power of human ingenuity and the scientific method. These capabilities didn't exist even 20 years ago, and they're improving rapidly. As you look up at the night sky tonight, remember that many of those stars have planets orbiting them. Statistics suggest that virtually every star you can see has at least one planet, and many have multiple worlds. Some of those planets are undoubtedly lifeless rocks too hot or too cold for habitability. But others, a precious few, might be worlds not so different from Earth. They might have blue skies above liquid water oceans. They might have weather systems with clouds and rain. They might experience day and night cycles, seasonal variations, and climate zones. And they might have life, perhaps simple microbes in the early stages of evolution, perhaps complex ecosystems with organisms as diverse as Earth's rainforests, perhaps even intelligent beings looking back toward us across the light years. Those worlds are out there right now, and we're finally beginning to find them. The discoveries we make in the coming years and decades will reshape our understanding of life, planets, and our place in the cosmos. This is the beginning of an extraordinary journey of discovery, and you're here to witness it unfold. The James Webb Space Telescope has given us eyes to see what was previously invisible. It has revealed ocean worlds like K2-18b, where alien seas might stretch from horizon to horizon. It has shown us super-Earths like LHS 1140b that sit in the perfect zone for habitability. It has allowed us to study entire planetary systems like TRAPPIST-1, where 7 worlds orbit a single tiny star. And it has brought our nearest neighbouring planet, Proxima Centauri b, within reach of detailed study. Each of these worlds tells a story about how planets form, how atmospheres evolve, and where life might take hold. The data flowing back from Webb is more than just numbers and spectra. It represents humanity's expanding understanding of the universe and our place within it. Every molecule detected in an alien atmosphere, every temperature measured on a distant world, every orbit traced around a faraway star adds to our collective knowledge. This knowledge isn't just academic curiosity. It informs how we understand our own planet, how we predict its future, and how we might ensure our civilization's long-term survival. We're living through a revolution in astronomy comparable to when Galileo first turned a telescope toward the heavens and discovered moons orbiting Jupiter, proving that not everything in the universe revolves around Earth. We're experiencing a shift in perspective as profound as when Copernicus showed that Earth orbits the Sun rather than the other way around. The discovery that potentially habitable planets are common throughout the galaxy, that liquid water oceans might exist on the worlds circling other stars, and that the chemical signatures of life might be detectable across light years of space represents a fundamental transformation in how we understand our cosmic context. The younger generation growing up with these discoveries will have a fundamentally different worldview than previous generations. They'll learn about exoplanets in elementary school, alongside learning about the planets in our solar system. They'll grow up knowing that the stars they see at night have planets around them, that some of those planets might harbour life, and that humanity has the technology to study those distant worlds. This generation might be the one to receive confirmation that life exists beyond Earth, a discovery that will rank among the most important in human history, alongside the development of agriculture, the scientific revolution, and the exploration of our own solar system. The questions that drove ancient philosophers and that inspired generations of science fiction writers are now questions we can answer with observations and experiments rather than speculation and imagination. Are we alone in the universe? We don't know yet, but we have the tools to find out. How common is life? The data is accumulating that will let us answer this question statistically rather than guessing. What forms does life take on other worlds? We might discover alien biochemistry radically different from anything on Earth. Or we might find that life everywhere uses similar chemistry because those are the molecules that work best. Can civilizations survive and thrive for millions or billions of years? If we find evidence of technological civilizations older than ours, we'll know it's possible. These aren't idle questions. They touch on the deepest issues of meaning, purpose, and existence that humans have always grappled with. The answers will shape philosophy, religion, art, and culture in ways we can barely anticipate. They'll influence how we think about our responsibilities to preserve life, whether on Earth or potentially on other worlds. They'll inform debates about planetary protection, about whether and how we should communicate with alien intelligences if we find them, and about humanity's long-term future among the stars. The James Webb Space Telescope is scheduled to operate for at least 20 years, and possibly longer if its systems remain healthy and its fuel lasts. During that time, it will continue to observe the most promising potentially habitable exoplanets, building up data sets that span years and allow us to watch these worlds change over time. We might see seasonal variations as planets orbit their stars, atmospheric changes that could indicate biological processes, or even more dramatic events like asteroid impacts or volcanic eruptions that reshape atmospheres in real time. Each year of observations will add to our understanding and bring us closer to definitive answers about habitability and life. But Webb is just the beginning. The next generation of telescopes, both on the ground and in space, will push the boundaries even further. Within 20 years, we should have telescopes capable of directly imaging Earth-sized planets around nearby Sun-like stars, seeing them not as points of light, but as actual worlds with visible features. We might see continents and oceans, weather patterns and seasonal changes, maybe even vegetation if it exists. These direct observations will complement Webb's spectroscopic studies and provide a more complete picture of what these worlds are actually like. The search for life beyond Earth is entering its most exciting phase. For the first time in human history, we're not just wondering whether life exists on other worlds. We're actively searching for it with instruments capable of detecting it if it's there. The biosignatures we might find could come from microbes similar to the bacteria that dominated Earth for billions of years before complex life evolved. Or they might come from more complex ecosystems, alien forests, or algae blooms covering vast oceans. The possibilities are extraordinary and diverse, limited only by what chemistry and physics allow and what evolution can produce given billions of years and countless environments. If and when we do discover life beyond Earth, whether on an exoplanet, hundreds of light years away, or on a moon in our own solar system like Europa or Enceladus, that discovery will mark a before and after in human civilization. It will answer one of humanity's oldest questions and immediately raise countless new ones. What is that life like? How did it originate? Is it related to Earth life through panspermia? Or did it arise independently? How complex is it? Can we learn to communicate with it if it's intelligent? These questions will drive research for generations to come. Even if we search for decades and don't find clear evidence of life, the search itself is worthwhile and will produce valuable knowledge. We'll learn what factors make planets habitable or uninhabitable, which types of stars are most likely to host life-bearing worlds, and how common or rare the conditions for life really are. We'll develop a much more sophisticated understanding of planetary atmospheres, climate systems, and the long-term evolution of planets over billions of years. All of this knowledge will help us better understand and protect Earth, our one confirmed habitable world. The story of the James Webb Space Telescope's discoveries of potentially habitable exoplanets is still being written. Every observation adds a new chapter. Every detected molecule tells us something new. Every measured temperature refines our understanding. The planets we've discussed in this video, K2-18b with its possible ocean and tentative biosignatures, LHS 1140b with its optimal location and potentially Earth-like atmosphere, the 7 worlds of TRAPPIST-1 offering a natural laboratory for comparative planetology, Proxima Centauri b right next door in cosmic terms, and all the other worlds Webb has studied represent our best current understanding of where to look for life beyond Earth. But tomorrow's observations might reveal new worlds even more promising than these. There are thousands of known exoplanets and probably billions in our galaxy that we haven't found yet. Among those billions of worlds, some are surely more Earth-like than anything we've discovered so far. Some might have conditions even better suited for life than Earth provides. Some might already host thriving biospheres that have existed for billions of years, evolving in directions we can't predict and producing forms of life we've never imagined. The universe is far larger and more diverse than our small sample of planets can reveal, and the discoveries ahead will continue to surprise us. The James Webb Space Telescope has shown us that we live in a universe full of worlds, not just barren rocks and gas giants, though those are common enough, but potentially habitable planets with atmospheres, with water, with the chemical ingredients for life, and possibly with life itself. These worlds orbit stars throughout the galaxy, from nearby systems just a few light years away to distant stars hundreds of light years distant. They come in varieties we never imagined, from ocean worlds covered in global seas to super-Earths with exotic atmospheres, from tidally locked planets with eternal day and night sides to worlds orbiting in resonance with their neighbours. We're fortunate to live in this moment when the technology has finally caught up with humanity's ancient dreams of exploring other worlds and searching for life among the stars. Previous generations could only wonder and imagine. Future generations will grow up with the answers we're discovering now and will build on our work to explore even deeper into space and study even more distant worlds. But we're the generation that's making the transition from speculation to observation, from wondering if other Earths exist to studying specific planets that might harbour life. That's an extraordinary privilege and responsibility. As this video ends and you go about your day, remember that the universe is far stranger and more wonderful than we once thought. Remember that there are planets out there with skies of colours we've never seen, with sunrises illuminating landscapes no human has ever witnessed, with weather patterns driven by physics we're still learning to understand, and possibly with life following evolutionary paths completely different from anything on Earth. Those worlds are real, they exist right now, and we're finally developing the ability to study them. The quest to find life beyond Earth and to understand our place in a universe full of worlds has only just begun. The James Webb Space Telescope has given us the first real glimpses of potentially habitable exoplanets, but so much remains to be discovered. In the years ahead, as telescopes grow more powerful and our techniques more sophisticated, the discoveries will accelerate. We'll learn which of the planets we've found are truly habitable, we'll detect more biosignatures, or confirm that the tentative ones we've seen are real, and we might even find definitive proof that life exists beyond Earth. This is the most exciting time in the history of astronomy and arguably in all of science. We're on the verge of answering questions that humans have asked since we first looked up at the night sky and wondered what was out there. The answers are beginning to come in, and they're more exciting than we dared to hope. The universe is full of worlds, and some of them might be even better than Earth. Welcome to the golden age of exoplanet discovery. Welcome to the era when humanity finally begins to understand its cosmic context. Welcome to a universe transformed by discovery. The exploration continues, the observations never stop, and the next great discovery could come at any moment. Stay curious, keep looking up, and remember that we're all part of this incredible journey to understand the cosmos and find our place among the stars.